Hello, good morning everyone. So this is Pratibha and again welcome to, as you know, that PG Physics classroom. Sorry, since 2 days I couldn't upload the videos due to some issues. So sorry for that. Let us continue with the new topic. So just revising the previous topic, whatever we have discussed in earlier classes. Okay. So log ft values, I have told you that ft is nothing but what? Comparative half-life. The product f into t is called as comparative half-life, and depending on the basis of those log ft graph, we differentiate the transitions, beta rate transitions, whether the transition is allowed or forbidden, first forbidden, second forbidden, like that, super allowed, simply allowed, first forbidden, second forbidden, third forbidden. So these all transitions we are differentiated by using the value of log ft value. So as you know, that is log ft value. If suppose log ft value, or whatever the decay element you can take, if it tends for the value log ft 3 to 4, then you can say super allowed. So then 4.5 to 5 simply allowed. So greater than that, first forbidden, second forbidden, like that. Okay, now let us continue with the beta decay selection rules. Just wait a moment, I will open that document. Okay, I hope this video is clear. I think. Okay, sorry, last video is not that words are not clearly seen in the earlier video, so you can refer the Ghoshal book. So Ghoshal book in the 126 page number 118, 19, 119, 120, 121, like that. So okay, up to this much we have discussed. That is, the probability for the allowed transition depends on the nuclear matrix. So as we discussed in earlier class, if this happens to be 0, then we have to consider the higher order terms in the expansion of leptonic wave function for electron and neutrino. Uh, as we saw, the next higher order term is lower by a factor 1 divided by 10, so that the probability of this first forbidden transition is lower by a factor of 1 divided by 100. So this is small compared to the probability of the allowed transition. It is not as small as in the case of radiative transition in the atoms, for which is equals to r by lambda cross square is equals to 10 raised to minus 6. So the forbidden transitions are more important for beta decay. If the second term in the expansion also gives a value 0 for matrix element, then we have to take the third term corresponding to the second forbidden transition with the probability lower, again by a factor 1 divided by 100. For successive higher order terms in the expansion, we get the third, fourth, etc. Forbidden transitions, the probability in each case being a lower by a factor 1 divided by 100 than in the previous order. The orbital angular moment are carried away by the emitted particles are 1, 2, 3, etc. Units of for the first, second, third, etc. forbidden transitions respectively. In evaluating the matrix element of the transitions, another correction has to be taken into account, which was not considered above. This is a relativistic correction term, which is of the order nu by c, and which should be present in the matrix element. Nu being the velocity of the nucleons, since the square of the so fixed element is involved in the probability of transition, and since nu by c is nearly 1 by 10, this correction results in terms again 1 divided by 100, which is as large as the other correction term. So now that is important, log ft graph, and depending on that graph values, you have to differentiate the different modes of beta transition, allowed, super allowed, and first forbidden, second forbidden, like that. So now today also, whatever we are going to discuss, the topic, that is selection rules in beta decay, this is also important topic, and they definitely ask, write a note on selection rules. How do you select the element to decay, beta decay process? So write down the selection rules for beta decay process. Like that the question will arise. The beta transitions are governed by certain selection rules depending on whether the beta decay is allowed or forbidden. A nuclear state is characterized by the total angular momentum I and the parity pi. So parity can be calculated as what? Pi is equals to, that is minus 1 raised to L, where L being the orbital angular momentum. So now the total angular momentum or the spin of the nucleus is the vector sum of the orbital and spin angular momenta. As you know, I is equals to L plus S. When all the transition takes place from an initial state to a final state, we can write the change in I, total angular momenta, that is del I equals to IF. IF means final state. Spin for the final state minus II, spin for the initial state, such that del I is equals to del L plus del S. Please write down the equations. As we have seen, the electron and the neutrino wave functions can be represented by the plane waves if the Coulomb effect is neglected for the electronic wave function. In the expansion of the plane wave, the first term gives the allowed transition, which corresponds to the emission of beta electron and neutrino in the S state with L is equals to 0. See here. Wait a minute. Okay. In the expansion of the plane wave, the first term gives the allowed transition, which corresponds to the emission of electron and neutrino in the S state with L is equals to 0. This can be seen writing, that is plane wave function can be written as phi is equals to exponential of I k into R, k being the wave vector. So exponential of k in terms of the momenta, we can write P bar H cross into R. So this is nothing but what? Exponential of this one e raised to x, 1 plus x square plus x cube, like that. So expansion of Taylor expansion of e raised to x, that is 1 plus x 1 plus x square plus x cube, like that. Now PR is a measure of the orbital angular momentum. PR is a measure of the orbital angular momentum, which is in quantum theory can be written as LH cross, L being the orbital angular momentum, quantum number of the emitted electron and neutrino, neglecting all but the first term in the expansion. Then amounts to taking only L is equals to 0 term, since R is equals to 0 for this. The higher order terms correspond to higher values of L. The orbital angular momentum carried away by the electron neutrino pair must be equal to the change del L of the nucleus in beta negative transition. So for allowed transition, del L equals to 0. For the allowed transition, please do remember, that is del L and small l, that is orbital angular momentum, equals to 0. Then from the equation, this equation 5.91, this equation, we get for allowed transition del L is equals to del S. So in figure, I will show you a figure. We show that vector diagram for the angular momentum change in beta transition. If initial spin and final spin are the nuclear spin vectors of the initial and final states in the transition, then del I is equals to, as you know, difference in the final and initial state, so that IF can be written as you know. So del I is equals to what it is? IF minus II, so that IF can be written as IF is equals to, again, del I plus II, okay, like that. So as shown in the figure, I will show you a figure for the allowed transition. Since del L equals to 0 and del I equals to del S, the corresponding vector diagram should be as shown in figure. The electron and neutrino are spin half particles. Their spins can be aligned either parallel or anti-parallel to each other. So wait for a moment, I will go to the next slide. Okay, please draw these diagrams. So this is 5.19, a vector diagram for the change of nuclear spin in beta transition, and B with change of I in the allowed transition. C and D, these are alignment of the electron neutrino spins, parallel and anti-parallel. The total spin angular momentum carried away by them, C and D, can be either S is equals to 0 for parallel or S is equals to 1 for anti-parallel. See, so S is equals to 0 for parallel and S is equals to 1 for anti-parallel. In the first case, the spin change of the nuclear state will be del I del S equals to 0. This corresponds to what is known as the Fermi selection rule. This corresponds to what? The Fermi selection rule. In the second case, del I del S is equals to 1. Del I del S is equals to 1, which corresponds to what? Gamow-Teller selection rule. Please to remember, these two law selection rules are very important in beta decay transition. Fermi two type selections rules are there: Fermi selection rule and Gamow-Teller selection rule. In the Fermi selection rule, what happens here? Del I is equals to del S is equals to 0. This corresponds to what? Fermi selection rule. And del I del S is equals to 1. This is corresponds to Gamow-Teller selection rule. The possible changes in the nuclear spin in the case of Gamow-Teller selection rule are shown by the vector diagram in the figure 5.20. You can see here. Nuclear spin changes in the case of a load Gamow-Teller selection rule. These are the diagrams for Gamow-Teller selection rule. So another one is Gamow-Teller selection rule. So here where the spins of the neutrino and electron are parallel in nature. So as you know, this is parallel in nature, and del I del S is equals to 1. And B, I will discuss you. The possible changes in the nuclear spin in the case of Gamow-Teller selection rules are shown by the vector diagram in figure. From the figure, it is clear that the change in I can have the values del I is equals to 0, plus or minus 1. In this case, it may be noted that in the Gamow-Teller selection rule, the transition cannot take place from the state II is equals to 0 to the IF is equals to 0. 0 to 0 transition cannot be possible in the Gamow-Teller selection rule, because this transition involves the spin angular momentum change of 1 unit. As stated before, the nuclear states are also characterized by the parity. For states of with even odd L, the parity is even. States are even, then parity is even. If the states are odd, the parity is odd, since no change of L takes place in case of allowed transitions. So there is no change of parity. This is expressed by the word no in the above selection rules. To illustrate the above selection rules, we take the case of beta decay of helium, 6 helium. You can see here 2He6, which undergoes beta negative transition. What you will get? Lithium. Here you can see here 2He6, the spin is 0 and parity is positive. Here spin is 1 and parity is positive. Parity does not change for the Gamow-Teller selection rule. There is a spin change, del I is equals to I. There is a spin change, not a parity change, without any change of parity in this transition. So this transition is governed by pure allowed Gamow-Teller selection rule. That it is an allowed transition is confirmed by the Ft value as given in the table. So yesterday we shown that table, that is log Ft table. So you can refer that table, then you came to understand. So which shows it to be super allowed. An example of pure Fermi selection rule is observed in the decay of oxygen 14. See here. So we'll explain regarding the Fermi selection rule later. So this is up to what the Gamow-Teller selection rule. Parity will not change, only the spin change takes place, and also the angular momentum will also not changes. And for the even states, the parity is even. For the odd state, the parity is odd. So these are the diagrams which represents the Gamow-Teller selection rule. Okay, I hope up to this you are clear. Okay. Fermi selection rule. Wait a moment.